Good morning. In this session, we are going to see a topic on two-dimensional steady-state conditions on heat transfer. Heat generated during the process is absorbed by the medium, due to which the temperature of the medium rises. The temperature of the medium rises till the steady operating conditions are reached and rate of heat generation equal to the rate of heat transfer to the surrounding. There are heat transfer applications that involve the conversion of some form of energy into thermal energy into medium. Such medium are said to be involved internal heat generations. In heat conduction, with uniform heat generation problems, the quantities of major interest are the surface temperature and the maximum temperature that occurs in medium under steady operation conditions. In such case, for a 2D steady state situation, the heat equation is simplified is d by dx. It needs two boundary conditions in each directions. There are three approaches to solve this equation. First one is a numerical method, graphical method, and third one is a analytical method. In numerical method, the finite difference or infinite element schemes usually will be solved using computers. In graphical method, it is a limited method. However, the shape factor concept derived under the concept can be used for specific configurations. In analytical method, it is a mathematical equation and it can be solved through the mathematical process. The conduction shape factor. The approach applied to 2D conduction involving the isothermal surface, with all the other surface being the heat transfer from one surface at the temperature to the other surface, can be expressed. The shape factor can be related to the heat inside the plane wall of the thickness. For example, the oil pipeline is buried in the earth at a depth of 1 meter. The horizontal pipe is thin walled of outside diameter 50 cm. The pipe is very long and average temperature of the oil is 100 degrees Celsius. Estimate the heat loss per unit length of the ground soil temperature is minus 20 degrees Celsius. We can see the diagram from the table from HMD data book. We can take a formula S is equal to 2 pi L by ln 4Z by D. Then the value of L is equal to 1 and the Z is equal to 0, 1. Sorry, D is equal to 0.5. The value is 1.81.2 watts. Next problem. If the mass flow rate is 2 kg per second and the specific oil is 2 kJ per kilogram Kelvin, the heat of temperature change in 1 meter, determine the pipe length. The formula is Q is equal to M into Cp into delta T, and the value is 0.045 degrees Celsius. Therefore, the total temperature variation can be significant pipe if it is very long. For example, 45 degrees Celsius for every 1 kilometer of pipe, and the heating might be needed to prevent the oil from freezing up. That's the diagram. From that, the temperature drops exponentially from the initial temperature of 100 degrees Celsius. It reaches a 0 degrees Celsius at H is equal to 4740 meter. Therefore, the reheating is required for every 4.7 kilometer. Thank you.